Hey everybody, a new topic in calculus, absolute maximum values and absolute minimum values. Here's our definition of absolute maximum value. The real number, capital M, is the absolute maximum value of the function f of x exactly when these two conditions both hold. First of all, our absolute maximum value, capital M, has to be greater than or equal to f of x for all values of x. And for some x value, x equals c, f of c equals the absolute maximum value, capital M. Now, the point of this stipulation is that in order for capital M to be the absolute maximum value of the function f of x, then f of x actually has to be equal to the absolute maximum value for some value of x. Let's say x equals c. Now, in plain speak, m is the largest value that f of x attains. And notice, again, the absolute maximum value m has to be a value that the function attains. So there has to be some x value that we can plug into f of x and get capital M, the absolute maximum value. Now, before we do any examples, I'm going to define the analog of the absolute maximum value, and that's the absolute minimum value. Here's the analog, the absolute minimum value of a function f. And essentially I've kept everything the same on the board, except I've altered the statements so that we can define absolute minimum value. The real number little m is the absolute minimum value of the function f of x exactly when these two conditions hold. First of all, the absolute minimum value, m, has to be less than or equal to f of x for all values of x. And then for some x value, x equals c, f of x is actually equal to the absolute minimum value. And the stipulation here is, in order for a function to have an absolute minimum value, little m, the function actually has to equal the absolute minimum value for some value of x. There has to be a value of x, let's say x equals c, that we can plug into this function and actually get the absolute minimum value. So we can say that little m is the smallest or least value that f of x attains. And again, when we say attains, we're saying there has to be a value of x that we can plug into the function to get this absolute minimum value. There. Now that we've gone through all of the definitions, let's look at a truckload of examples. And I'm not exaggerating. Okay, our first example. F of x equals x squared over x squared plus 1. Excuse me. Now, let's do the absolute minimum value first. Is there an absolute minimum value? What do you think about that? Is there a smallest value that f of x attains? If you're thinking that y equals 0 is the smallest value, then you're right. The absolute minimum value is 0. It's the smallest value or the least value that f of x attains. And I'm going to put something else here also. I'm going to give the x value at which the absolute minimum value is attained. So the absolute minimum value is 0, and it's attained at x equals 0. What about an absolute maximum value? If there is one, I guess it would be 1, right? But here's the catch. Does f of x ever actually equal 1? Y equal 1 is a horizontal asymptote, and as we move along the graph with x going to infinity, the graph gets closer and closer and closer to this asymptote y equal 1. But does it ever actually get there? Well, think about it this way. F of x is a quotient, isn't it? And in order for this quotient to be equal to 1, the numerator and the denominator would have to be equal. Can that happen? And the answer is no. The denominator is always going to be 1 unit larger than the numerator. So in fact, f of x is always less than 1. So this graph never actually touches the line y equal 1. And f of x never actually becomes equal to 1. But son of a gun, it gets arbitrarily close, doesn't it? The limit of this thing as x goes to infinity is 1. This function gets closer and closer and closer to 1, arbitrarily close to 1, but it never gets there. So is there a real number, capital M, such that f of x is less than or equal to capital M? Is there a smallest real number, capital M, such that f of x cannot become equal to capital M or cannot be greater than capital M? Yeah, capital M equal 1. Every f of x value is less than or equal to capital M equal 1. But f of x never actually becomes equal to 1. So even though we're tempted to say the absolute maximum value of f of x is 1, it's not the absolute maximum value of the function because there's no value of x that will make f of x equal to 1. So absolute max value none. This function has no absolute maximum value. Now there is something else I'd like to draw your attention to. The point right here where we have the absolute minimum value. I'm tempted to say that on the graph of f of x, this is a relative minimum. And if it is, that means that x equals 0 should be a critical number, right? Let's check that out. So I'll say q is x equal, no, let's see, is 0, 0 a relative max also? or relative min rather. So in other words, not only does f of x attain the absolute minimum value here at the point 0, 0, we want to know, is the point 0, 0 a relative minimum also? If it is, that means that x equals 0 would have to be a critical number, because we know that we don't get relative maxes or mins unless we have a critical number at that point. So let's see. Let's compute the derivative. And we get top prime times the bottom minus bottom prime times the top all over the bottom squared and we have 2x cubed minus 2x cubed is 0. 2x times 1 is 2x. So f prime of x is 2x over x squared plus 1 squared. And f prime of 0 is equal to 2 times 0 over 0 squared plus 1 squared, which is 0. We plug x equals 0 into the derivative and we get 0. That means that 0 is a type A critical number. So for future reference, this is something that we want to remember. And I'm going to write this down. I'll let you look at the computations for about 10 seconds. I'll erase them and I'll write my comment right under here. Note, x equals 0 is a critical number and 0, 0 is also a relative min. We don't want that fact to escape our notice. There is oftentimes a relationship between relative maxes, relative mins, and absolute maximum values and absolute minimum values. So as we look at our examples, anytime that we see an absolute maximum value or an absolute minimum value occurring at a critical number, and therefore a relative max or a relative min, we want to take notice, because that observation or those observations will come in handy later on in this discussion. New example. F of x equals x squared plus 2x plus 1. This is what the graph looks like. First of all, are there maximum values? Is there an absolute maximum value, a largest value? And we look at this thing and we go, well, hey, this graph takes off and it goes to positive infinity. So maybe positive infinity is the absolute maximum value. So let's try that. And I'll put a question mark over that. Is the absolute maximum value equal to positive infinity? If so, there has to be an x value that I can plug into this function to get positive infinity. There has to be a real number value of x that I can plug into this function and get positive infinity. And that's not going to happen. And let's put down a reason. In order for this to be an absolute maximum value, or the absolute maximum value of f of x, there has to be some real number, x equals c, that we can plug into this function and get positive infinity. But is there such a real number? No. No matter what real number we plug in here, we're going to square it, we're going to multiply it by 2, we're going to add 1, and we're going to get some other real number. Plug a real number in here, we're going to get a real number out here. We're not going to get plus infinity. So, absolute maximum value there is none. Yikes. This is the second example in a row where we've had no absolute maximum value. Absolute minimum value? Absolutely. When x equals -1, f of x equals 0, and this is the lowest value, this is the smallest value that f of x can assume. So little m equals 0, and parenthetically I'll also mention the value of x at which this is attained. Now, is this thing also a relative max? Well, let's see. Let's transfer this up. Absolute min value. Little m equals 0. Attained at x equal -1. If this is a relative min, then x equal -1 has to be a critical number. Let's see. We'll compute the derivative, f prime of x, and we're going to get 2x plus 2. Oh, and when we plug -1 in there, what happens? f prime of negative 1 is 2 times negative 1 plus 2 equals 0. Negative 1 is an x value that makes the derivative 0, so yes. X equal negative 1 is a type A critical number, and the point negative 1, 0 is also a relative min. So again, not only do we have an absolute minimum value, but right here where the absolute minimum value is attained, we have a critical number and a relative minimum. That's going to be important to remember. Another example, f of x equals negative x squared minus 2x. Here's the graph. First of all, let's see if there's an absolute minimum value. Well, look at this graph. It just goes down to negative infinity. So if there is an absolute minimum value, it's going to be negative infinity. But if negative infinity is the absolute minimum value of this function, there ought to be an x value that we can plug in here and get negative infinity. Is that going to happen? So here's a function that has no absolute minimum value. What about an absolute maximum value? What do you think? Right here, f of x, whoops. Well, I took my vitamins this morning, and I guess along with my vitamins, I remembered to take my stupid pill too. I've definitely had my stupid pill today. There, how about that? This makes a lot more sense, doesn't it? So it looks like we have the absolute maximum value attained at this point. And what is the absolute maximum value? It's positive 1, isn't it? So let's write that down. Capital M equals positive 1. And let's also note the x value where it's attained. Now, why is this so important? Why do we need to know the value of x where we've attained the absolute maximum value? Well, let's look at it this way. Suppose we have a profit function. Then we're going to want to know what the absolute maximum profit is. But we're going to want to know more than that. Not only are we going to know what the absolute Not only are we going to want to know what the absolute maximum profit is, but we also want to know the x value, the level of production, the x value that will take us to that absolute maximum profit. It's not going to do us much good to know the absolute maximum profit if we don't know the x value that will get us that absolute maximum profit. So when we find our absolute minimum and maximum values, we also want to note the x value at which they're attained. This is going to be important. Now again, we want to ask the question. We have the absolute maximum value attained at this point. Is this also a relative maximum? And in order for this to be a relative maximum, then x equal -1 has to be a critical number. So let's check it out. Let's compute the derivative of this thing. F prime of x is -2x minus 2. And let's just take -1 and plug it in here and see what happens. So we get 2 minus 2 is 0. Yup. When we plug -1 into the derivative, we get 0. So that tells us that x equal -1 is a type A critical number. And what? -1, 1 is a relative max. So not only is the absolute maximum value attained at this point, but it's also a relative maximum. And the x value at which we attain this absolute maximum value is a critical number. Oh, we brought out the dreaded sine function. Well, does this have an absolute maximum value and an absolute minimum value? What's the largest value that the sine of x can attain? Isn't it 1? And at x equal pi over 2, sine of x is 1. At x equal 5 pi over 2, sine of x is 1. At x equal 9 pi of 2, sine of x equals 1, and off into the sunset. And what about the relative minimum values, or no, absolute minimum value? It looks like the absolute maximum value is 1, and sine attains that at x equal pi over 2, x equal 5 pi over 2, x equal 9 pi over 2, and so forth. And absolute minimum value of sine of x, the smallest value that sine of x can attain, -1, right? And that happens when x is negative pi over 2. It happens again when x is 3 pi over 2. It happens again when x is 7 pi over 2. And so on and so forth on into the sunset. So here's a function that has both an absolute maximum value and an absolute minimum value. So absolute max value m equals 1, and we'll note that it's attained at x equal ... pi over 2, 5 pi over 2, 9 pi over 2, an absolute minimum value, -1. Absolute minimum value, little m equals -1. And we'll note parenthetically that it's attained at x values negative pi over 2, 3 pi over 2, 7 pi over 2, and so on and so forth on into the sunset. So here's an interesting example because the absolute maximum value is attained in more than one place. Here, here, here. As a matter of fact, the absolute maximum value is attained at infinitely many points on this graph. And the same thing with the absolute minimum value. The absolute minimum value is attained here, it's attained here, it's attained here, and so on. The absolute minimum value is attained at more than one place on the graph. Infinitely many, in fact. So here's a function that has both an absolute maximum value and an absolute minimum value. And the absolute maximum and minimum values are attained in more than one place on the graph. Now there's something else that we should note about this before I erase everything. All of these numbers at which the absolute minimum and maximum values are attained turn out to be critical numbers. So all of these are critical numbers. And it turns out all of these are critical numbers too. And so that means that wherever we have a relative maximum or a relative minimum, wherever we have an absolute maximum value attained or an absolute minimum value attained, that point on the graph is also a relative maximum or a relative minimum. So far, every place that we've attained an absolute maximum value has been a relative maximum. Every place where we've attained an absolute minimum value has been a relative minimum. Let's look at one more example. This is a good example. F of x equals x cubed. And notice for positive values of x, this graph takes off and goes to infinity. For negative values of x, again, this graph takes off and goes to negative infinity. So is there a largest value that this function attains? No. Is there a least value that this function attains? No. So do we have an absolute maximum value? No. Do we have an absolute minimum value? No. This is a function that has neither an absolute maximum value nor an absolute minimum value. I wonder if it has any critical numbers. Let's see. F prime of x is equal to 3x squared. And if we set the derivative equal to 0, that tells us that x equals 0 is a type A critical number. So right here, we have a critical number, but we don't have a relative maximum or a relative minimum here. And we certainly don't have an absolute maximum value attained here, or an absolute minimum value attained here. So here's a somewhat unusual situation. We have a critical number, x equals 0. Nothing much seems to happen there. We don't have a relative maximum here. We don't have a relative minimum here. And our function has no absolute maximum value, no absolute minimum value, no absolute max, no absolute min. If we put all of these examples together, we can come up with some pretty important conclusions. So let's do that. Here are some important things to observe about absolute maximum values and absolute minimum values. The first thing, a function may have both an absolute maximum value and an absolute minimum value. It may have both. Or a function may have one but not the other. It may have an absolute maximum value but no absolute minimum value. Or it may have an absolute minimum value but no absolute maximum value. Or it could be that the function has neither an absolute maximum value nor an absolute minimum value. So again, a function may have both an absolute max value and an absolute min value. Could have one but not the other, or it may have neither. The second observation, the absolute maximum value or the absolute minimum value may be attained at more than one point on the graph of f of x. And all we have to do to be convinced of that is just remember what happens with the sine function. The absolute maximum value of sine of x is 1. And the absolute minimum value of sine of x is -1. And what does that function do? It keeps bouncing back and forth between -1 and +1 off into the sunset. It attains the absolute maximum value of 1 at infinitely many points on the graph. It attains the absolute minimum value of -1 at infinitely many points on the graph. So the absolute maximum value or absolute minimum value may be attained at more than one point on the graph. And we were keeping count for this third point. So far, all of our absolute maximum values and absolute minimum values have occurred at critical numbers. So wherever we've had an absolute maximum value, we've had a relative maximum. Wherever we've had an absolute minimum value attained, we've had a relative minimum value. And at each of these places, there have been critical numbers. So far, we haven't seen an absolute maximum value any place where there wasn't a critical number. We haven't seen an absolute minimum value attained at any point where there wasn't a critical number. So do they necessarily have to go hand in hand? Well, let's see. Let's go back and look at the function f of x equals x cubed. That function had neither an absolute maximum value nor an absolute minimum value. Here's the function f of x equals x cubed. And we want to restrict it to the closed interval from -1 to 2 on the x-axis. So any part of the graph that extends to the right of x equal 2, we're going to chop that off. And any part of this graph that extends to the left of x equal -1, that we're going to chop that off too. And now let's ask ourselves this question. Does the graph have an absolute, or does the function, as it's defined here, have an absolute maximum value? And we look at the graph and we go, duh, the largest value is 8. And I'll say attained at x equal 2. Do we have an absolute minimum value here? Yep, the lowest point on the graph is right here where f of x equals -1. So the absolute minimum value is little m equal -1, and this is attained at x equal -1. Now, from working with the x cubed function before, we know that f of x equals x cubed only has one critical number, x equals 0. So these are not critical numbers. And the reason we know that x equals 0 is the only critical number. So this is not a critical number. This is not a critical number. And so that also means something else. The 0.28 is not a relative max. Why? Because we only have relative maximums and minimums at a critical number. And this is not a critical number. And so that also means that this point right here is not a relative min. Neither of these occur at critical numbers, so this can't be a relative max, this can't be a relative min. Well, it is a max. The largest value of the function, the largest value of the function is attained here. It is a max, but it's not a relative max because 2 is not a critical number. So what should we call it? Well, we might observe that this turns out to be the largest value of the function by virtue of the fact that after x equal 2, we chop off the function. And x equal 2 is the end point, the right end point of this interval. And to the left of x equal -1, we chop off the graph. So this point becomes the minimum value of the function because we've chopped the graph off at this left end point of the interval. So somebody in their great wisdom decided that we call this this 0.28 an endpoint maximum. And this point, -1, -1, is an endpoint minimum. Because they occur at the endpoints of the interval to which our function is restricted. Now, when we worked with x cubed before, it had neither an absolute maximum value or an absolute minimum value. And since we restricted it to this closed interval, all of a sudden it has both an absolute maximum value and an absolute minimum value. So let me stipulate exactly what we've learned from these examples. Okay, here's a major result. If f of x is continuous on a closed finite interval AB, then f of x attains both an absolute maximum value and an absolute minimum value, guaranteed, so let's see what the conditions are again. F of x has to be continuous, and the interval has to be closed. In other words, we use the square brackets here and not the round ones. So a and b are actually included in this interval. And the interval has to be of finite length. In other words, this can't be negative infinity and that can't be positive infinity. So if f of x is continuous on a closed finite interval, AB, then f of x attains both an absolute maximum value and an absolute minimum value, guaranteed. F of x has to have both. Furthermore, the absolute maximum value and the absolute minimum value must be attained at either a critical number or an endpoint. So under these conditions, f of x is continuous, this interval is closed and finite, f of x is going to have both an absolute maximum value and an absolute minimum value. And the only places that they can occur are at the critical numbers or the endpoints of this interval. So this is major. Now, usually at this time I give a speech, but I think I'm going to do a few examples first before I give my speech. But the speech is coming. Okay, here's an example. F of x is 2x cubed plus 3x squared minus 36x plus 5, restricted to the interval -2 to 3. And we're told use the absolute maximum minimum value test to find the absolute maximum and absolute minimum values of f of x. And you're probably saying, what is this absolute maximum minimum value test? And the answer is, I haven't told you yet. I'll use this example to outline the steps. And the first step is step 0. Step 0, determine whether the absolute max-min value test determine whether this thing applies. There are three conditions that have to be satisfied in order for this test to apply. The first thing is f of x continuous? Is it continuous? If it is, how do we know? And there's kind of an easy answer for this. Here's f of x. Is it continuous? What do you think? And probably the best way to show that this thing is continuous is to look at it and say, hello, this thing is a polynomial. All polynomials are continuous. Therefore, this is continuous. So, yes, f of x is continuous. F of x is a polynomial, so we know that it's continuous. Now, is it restricted to a closed interval? Yep, the interval's closed. It's got those square brackets up there, so -2 and +3 are included. Closed interval. And this interval, is it of finite length? Now, the only way that this interval could fail to be of finite length is if this endpoint were negative infinity or that endpoint were positive infinity. And that's not the case either place. So yes, the answer to all three of these things is yes. So the absolute maximum minimum value test does apply. So the first step is just to make sure that the test does apply. F of x has to be continuous, and it has to be restricted to an interval that's closed and of finite length. If these three conditions are satisfied, it's full speed ahead. Now let's go to step 1. Now, under these conditions, where f of x is continuous and it's restricted to a closed interval of finite length, we're guaranteed to have an absolute maximum value and an absolute minimum value. And there are only two places where they can be attained, either at the endpoints or at the critical numbers. We know what the endpoints are, so as our first step, let's find the critical numbers. prime is 6x squared plus 6x minus 36. And for type A critical numbers, f prime of c is 0. So we set the derivative to 0. These are big numbers, and every term has a factor of 6, so I'm going to divide both sides by 6. And I'm thinking x plus 3, x minus 2, does that work? 3x minus 2x is x. Beautiful. Okay, so here are my critical numbers. X equals negative 3 and x equals positive 2. And before I go further and make a fool out of myself, let me check something, because remember, we are working within a closed interval of finite length. In other words, f of x is restricted to this interval. Our function f of x doesn't exist outside of this interval. And let me check my critical numbers. Let's see, I'll write critical numbers here. X equal 2, yep, that's in there. X equal negative 3, oop, big problem. X equal negative 3 is not in this interval. So it was a candidate for critical number, but we're going to have to disallow it. Negative 3 is not an element of this interval. We have to throw it away. Now, there are such things as type B critical numbers, so let's look for those. And for our type B critical numbers, typically we look for an x value that causes division by 0 in the derivative. And here's our derivative. 6 times x squared plus 6 times x minus 36. We have multiplication, we have addition, we have subtraction, we have exponentiation. There's no division going on here anywhere. We're not dividing by anything anywhere here. So there's no way that we can be dividing by 0. No type B critical numbers. So it looks like x equal 2 is the only critical number. So we got our critical numbers. Now we go to step 2. We're going to take the critical numbers and the endpoints, and plug them into the original function, and here's why. The function's continuous. It's restricted to a closed interval of finite length. Under those conditions, we're guaranteed that our function has an absolute maximum value and an absolute minimum value. And there are only two places where this can happen, either at the endpoints or at the critical numbers. The absolute maximum value has to occur either at one of the endpoints or at the critical number. The absolute minimum value has to occur at one of the endpoints or at the critical number. So why not just take all of these things, the endpoints and the critical numbers, plug them into the original function and see which value is the largest and which value is the smallest. The largest value is going to be our absolute maximum value. The smallest value will be our absolute minimum value. So here we go. Plug the endpoint -2 into f of x. 2 -2 cubed plus 3 -2 squared minus 36 times -2 plus 5. Horror of horrors, what is that? See, this is 72 plus 5 is 77. Plus 12 is 89. Minus 16 is 73, I hope. That's what I'm thinking, 73. The critical number, that was 2, wasn't it? 2 cubed plus 3 times 2 squared minus 36 times 2 plus 5. Okay, this is 16 plus 12 is 28 plus 5 is 33, and this is -72. 39. I'm thinking -39 for that, I hope. And let's see. F evaluated at 3. 2 times 3 cubed plus 3 times 3 squared minus 36 times 3 plus 5. Now, what is that going to be equal to? Let's see. 3 cubed is 27 times 2 is 54. Plus 27 is 81. Okay, plus 5 is 86. Minus 108. So it looks like -22. And let me just check this again. -16. And we have what? 12 plus 72 is 84 plus 5 is 89 minus 16, 73. Okay, I'm pretty much convinced. Now, what's the significance of what we've done? We knew that we had to have an absolute maximum value and an absolute minimum value. And the only place where the function could attain these values was either at the two endpoints or at the critical number. So we plugged them into the function, knowing that one of these things has to be the absolute maximum value, and one of these things has to be the absolute minimum value. So we just looked for the largest value. This is the absolute max value. And this is the smallest value, absolute min value. So if we're wondering what our third step is, step 3, find the absolute max and min values by inspection. So absolute max value, $73, and I'm going to put attained at x equal -2. Absolute minimum value, little m equals -39. And this is going to be attained at x equal +2. And essentially, that's how we do our absolute maximum and minimum exercises when we have a continuous function defined on a closed interval of finite length. Now, when I was a student, this bothered my mathematical conscience. This sounds funny to say, but it really did. This really bothered me. And I looked at this and I thought, this is a cheap trick. You can take a function like x cubed, which has no absolute maximum value and no absolute minimum value, and all of a sudden turn it into a function that has an absolute maximum value and an absolute minimum value, just by chopping off the extremities of the graph, restricting the function to a closed interval like -1 to +2, for example. And I thought, that's a cheap trick. Hey, I can take this function that doesn't have an absolute maximum value and it doesn't have an absolute minimum value, and I can make it have an absolute maximum value and an absolute minimum value just by restricting it to a closed interval of finite length. Yeah, so what? To me, that was kind of like somebody going out and buying 13 decks of playing cards and taking the aces out of each deck and putting all of the aces together to form a deck of 52 cards, every one of which was an ace, and say, hey, bet you what? I bet you I can shuffle this deck and shuffle this deck and shuffle this deck. And see that? It's an ace. I'm going to shuffle again. I'm going to shuffle, 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 shuffle. I'm going to pick a card. See, it's an ace. I can pick an ace every time. Well, of course you can. Every card in the deck is an ace. It's a cheap trick. And to me, this bit about taking any function, any continuous function, and just restricting it to a closed interval and saying, hey, I can make this function have an absolute maximum value and an absolute minimum value just by restricting it to a closed interval. To me, this seemed like the same kind of cheap trick. And the problem was I wasn't really getting the motivation behind looking at a function restricted to a closed interval. I thought the whole idea of doing this was to take a function that didn't have an absolute maximum value and an absolute minimum value and to force it to have one of each just by restricting it to a closed interval of finite length. That's what I thought the motivation was. What I didn't realize was we look at continuous functions. restricted to a closed interval of finite length? Because in applications, more often than not, this models reality better than a continuous function that's not restricted to a closed interval of finite length. And I'll give you a hypothetical example, okay? Okay, here's my example. I own a factory that makes computers. Didn't know that, did you? Hypothetically, anyway. I own a factory that manufactures computers. X is the number of computers manufactured every day. And P of X is my profit function. And this makes sense. The profit is a function of the number of computers that I make. So profit is a function of X. Now, what is the smallest value that X can be? X is the number of computers produced per day. What's the smallest value that X can be? I can shut the operation down and manufacture nothing, right? I can produce 0 computers in a day. So X has to be greater than or equal to 0. I can't produce negative 15 computers per day. It's not possible. But I can produce 0 computers per day. That's possible. I just shut down the entire operation. Now, what's the most computers that I can produce in one day? I can't produce infinitely many computers. There are only finitely many atoms on Earth. So I can't produce infinitely many computers. There's got to be some number, capital N, beyond which I can't go. For example, let's say that all of the workers show up for work. All of the assembly lines run perfectly, no malfunctions. We don't have to shut down production for anything. Every worker does their job perfectly. There's a maximum number of computers that I can produce per day without either hiring more workers or expanding the production facilities, building extra buildings and putting in new assembly lines and so forth. But with the current number of assembly lines, the current number of workers, assuming that everything happens perfectly, there's a maximum number of computers that I can produce every day that I cannot go beyond without either hiring more workers or expanding the facilities or both. So, we'll assume that our profit is a continuous function, and we'll say that P of X is continuous on the closed interval 0 to n. And all of a sudden, this makes a lot of sense. I've restricted my function to a closed interval of finite length, but this models reality perfectly. I can't produce less than 0 computers per day. I can't produce negative 36 computers per day. I can't do that. And I can't produce infinitely many computers per day either. So actually, this model makes a lot more sense and is a lot more accurate than having my profit function being defined on the entire set of real numbers from negative infinity to positive infinity. Now, let's see what happens. here's my profit function, and X is the number of computers. Here's the origin. What happens if I produce 0 computers per day? Well, let's see. I probably still have to pay utilities. I still have to pay my workers. I may have to pay on the facilities that I'm renting if I don't own the facilities. So if I'm not producing any computers and selling any computers, I still have money going out, so I'm losing money. So my profit is in the negative numbers here. I'm losing money if X equals 0. Now, if I produce computers and I increase production, one of two things is going to happen. Either as I increase production, I'm going to hit this point right here, X equal capital N, and this is the high point of the graph. So this is my absolute max value, P of N. That's one scenario. I increase production to full capacity, and that gives me my maximum profit, P of N. That's one scenario. Now there's another scenario. When X is 0, I still lose money. And here's my capital N, the maximum number of computers I can produce. When production is 0 computers per day, I'm down here. So you bet I'm going to increase production. And that gets me out of the loss column, and I'm making money. But now maybe this happens. Maybe this happens. And my maximum, my absolute maximum value is at some critical number, C. Now, if I increase production, why would my profit increase until this point, and then all of a sudden start going back down? Well, maybe I'm making more computers than I can sell if my production level is over here. Maybe I'm producing more computers than I can sell. Right here, apparently, I'm producing exactly the number of computers that people are willing to buy. And then if I increase production beyond this point, I'm starting to make computers that people won't buy. I'm making too many. But it's still costing me money to make those computers. So I'm spending money to make computers. Nobody's buying these extra computers, so I'm actually losing money by increasing production to this level. Now here we have the absolute maximum value, and it's an endpoint max. Over here, I have the absolute max value. And note, the slope of the tangent is 0, so X equals C is a critical number. This is a relative max. And C is a critical number. These are the two scenarios. To get the maximum profit, I'm either going to have to increase production to maximum, and in this case, this is maximum production and I'm selling all the computers that I'm making. Or I increase production to the point where I'm selling all the computers that I'm making, but I'm not at maximum production. Here I have a relative max, and it gives me the absolute max value. Here I have an endpoint max. It gives me the absolute max value. And note, in each of these cases, my function p of x is restricted to a closed interval of finite length. So when I was a student, I got all bent out of shape about nothing. See, I thought the reason that we were restricting functions to a closed interval of finite length, was just so that we could force the function to have an absolute maximum value and an absolute minimum value. What I didn't realize was we were learning how to deal with functions defined on a closed interval of finite length, because when we do applications, more often than not, this is the situation that reflects reality and models reality. Well, what is an unrealistic situation? Having this function defined for the entire set of real numbers, where x, the number of computers produced, can go all the way to negative infinity, or x could go all the way to positive infinity. We allow this function to be defined on the entire set of real numbers, which means we can produce negative 50,000 computers a day. Really? How do you produce negative number of computers? Having our function defined on the entire set of real numbers very often is the unrealistic situation. And having our function restricted to a closed interval of finite length, very often that's the situation that models reality perfectly. So this is why we want to be able to work with functions that are restricted to a closed interval of finite length. And the good news is, if our function's continuous and it's restricted to an interval of finite length, there's always a largest value, there's always a smallest value. And I'm telling you that because I don't want you to get all bent out of shape like I did when I was a student. And I really did think that we were restricting our functions to closed intervals of finite length just to force the function to have a largest and smallest value. I thought it was a cheap trick, just like somebody buying 13 decks of cards, taking all the aces out and putting them together in one deck, and then going around and showing everybody that whenever they want, they can draw an ace from this deck. I thought this was the same kind of cheap trick as the deck of 52 aces. But it turns out there's a very good reason why we want to study continuous functions defined on a closed interval of finite length. Very often, in reality, this is what models the situation perfectly. And just think of it. If this is the interval that contains x, and x is the number of computers, can we manufacture a negative number of computers every day? No. Can we manufacture infinitely many computers every day? No. So having our profit function restricted to a closed interval from 0 to some positive number n, where this represents maximum production, that's actually the model that makes sense. And this is something that completely escaped me when I was a student taking calculus. But now that I've told you, hopefully you can appreciate why it is that we want to get very adept at finding absolute maximum values and absolute minimum values under these circumstances.